Hello and welcome to today's lecture. Today we will look into the Riemann-Hurwitz formula, which is a formula that relates geometric information about two curves via information about the behavior of a map between them. And this will lead us in the quest of finding a proof for this formula into the world of Kähler differentials. So let's get started. The idea is that if you have two reasonable algebraic curves and a map between them, you should be able to understand the geometry of one from the other. More specifically, the information about the morphism f should relate the genus of one of the curves to the genus of the other. The notions here are the degree of a curve and the ramification of the curve. We will define these in a minute, but the intuition one should have is that if you have a degree of a map, say you take something as simple as the map z goes to z to the power n, this should somehow be an n-winding of the object you have. So it should relate the genus, if you think about it geometrically, intuitively, the genus should be multiplied in some way by this degree. But the problem is that there is some error term to that, and that is points where there are ramifications. So, for example, if we look at the map z goes to z to the power n, then at each point, the pre-image, if you are working in an algebraically closed field, say on the complex numbers, the pre-image consists of n elements, except for 0, that only has 0 in its pre-image. And so there is something going on, there is some branching happening at 0. A more pictorial way is if you have something that looks like this, and then you project onto the line. Then everywhere you have a pre-image of 2 points, so generically this is somehow a 2-to-1 map, but over this point there is some branching or ramification going on. So we need to look into that a bit more. From now on, we will look at smooth, irreducible projective curves. So x and y will always be assumed to be smooth, irreducible projective curves. First, we start with the degree of a morphism. And we have a proposition that says that if we have a morphism between these curves x and y, then either it is constant or it is surjective. And if it is not constant, so surjective, then it is a finite morphism. And the induced map between the function fields, the rational function fields, defines a finite field extension. So the morphism being finite, so more precisely, finite means that it is finite on affine open. So we can cover the y with affine open sets vi. Then we look at f inverse vi. And these vi's, they correspond to some algebra. So the coordinate algebra is, say, bi. And this is ai. And so f star defines a map from bi to ai. And we want this to make ai into a finitely generated bi module, finitely generated as a module. So how do we prove this statement? Well, if f is not constant, then this means that f of x contains multiple points. So f of x, the cardinality is greater than 1. But f of x is a closed subset of y. This is because y is a projective variety, and we had this when we discussed completeness of projective varieties. So therefore f of x is closed, and also since x is assumed irreducible, then f of x is irreducible. This was an exercise at the beginning of the course, but closed irreducible subsets of an irreducible curve are either points, in that case sets of only one point, because if you have multiple points it is reducible, or the whole curve. So f of x is closed and reducible. So this implies that f of x is y. So f is surjective. To show that this is a finite field extension, this follows from the fact that both ky and kx, being the rational function fields of curves, they are finitely generated over k with transcendence degree 1. And from field theory, this implies that this is a finite field extension. So there is that. Next, to show that f is finite, take a cover of open sets of y and look at one such open affine set. So let v in y be open affine. Then the algebra O y of v, say, this sits inside the field, and so this injects via f star to k of x. And so you look at the elements in kx that are integral over this algebra. So you set B to be the subring of all, say, g in k of x that are integral over Oy of v. And in connection to the discussion on normalization, we have seen that this is a finite extension, and so this corresponds to an affine open U in X that is a finite module over Oy of V. And this precisely proves that F is finite. And so if F is surjective or non-constant, then we can define the degree of F to be the degree of the field extension that F defines. So henceforth, we assume that F is not constant, and then the degree is well defined. So there cannot be more points than the degree, because otherwise you would get a field extension of too high a degree. So you would hope that the number of points in the pre-image are equal to the degree, but if it is not, then you call it a branch point of F. So consider, for example, the map F from P1 to P1 that is defined by mapping x to x to the power n. So this means that it is induced by this map on affine patches. And since the function field of P1 is the rational function field in one variable, we get f star going in this direction, mapping t to t to the power n. So this means that it defines a field extension of degree n of this kt. So the intuition should be that the degree corresponds generically somehow to the number of points in the pre-image of any given point. So let's talk about exceptions to this intuition, namely branching and ramification. So if you take a finite morphism from x to y, x and y as before, smooth irreducible projective curves, then we call y a branch point if the pre-image of y has fewer points than the degree of f. So there cannot be more points than the degree, because otherwise you would get a field extension of too high a degree. So you would hope that the number of points in the pre-image are equal to the degree, but if it is not, then you call it a branch point of f. Next, we define the ramification index at a point x in x. So this is in some sense to quantify the amount of lumping together that happens when the when the point is in a pre-image of a branch point and there is some degeneracy going on. More precisely, if x is in x and y is the image of x, then the ramification index is the following integer. It's the discrete valuation at the point x of the uniformizer of the local ring at y. So let's unpack this definition. So we have f going from x to y. So it defines f star from oy of y to ox of x. And this defines a map in terms of the local stalks. So by localizing, you get a map from the local stalk at y to the local stalk at x. Now these are local rings, and since our curves are they are smooth, these are regular local rings, so discrete valuation rings. So the maximal ideal here, Iy, is generated by some element Ty. And this gets mapped to some unit times the generator of the ideal at x raised to some power that we call E sub x. So this is the ramification index. So if we look at an example, and now let me, although I'm considering a projective setting, let me take an affine example to get the idea across. So let's look at the map that squares x. And I'm assuming the characteristic is not 2 to make sense of this. Always in my examples, I'm assuming that the characteristic of the field is 0. So what happens here? Well, let's look at the point 1 here. So both 1 and -1 map to 1. So what happens with the uniformizer of the ideal at 1? Well, the ideal at 1 is generated by x minus 1. And when I pull it back along the squaring map, it will go back to the ideal x squared minus 1, which is x minus 1 times x plus 1. And so the valuation at 1 and at minus 1, the highest power of x minus 1 and x minus minus 1 in this element is 1. So I get E1 equals 1 and E minus 1 also equals 1. And this is what I would expect, because there is no ramification going on. The number of pre-images equals the degree. Whereas if I do this with the point 0, then the ideal at 0, which is x, goes to x squared. And x squared has valuation 2 at 0. So there is ramification at 0 of this point. So this is what this is all about. And so I want this EX to be 1. That means that there is no ramification going on. And so I say that there is a ramification or branching going on if EX is greater than 1. And then I call X a ramification point, and I say that F is ramified at X. And if now the characteristic of K is such that it divides this E sub X, then I call the ramification wild. Otherwise, I call it tame. And so if you work with good characteristic, meaning not causing this problem, then you work with tame ramification, and this is what we are going to do in the future. And one remark, so the set of ramification points is finite, basically by closedness. You can prove this yourself. And if you have a ramification point, then f of x is a branch point, because again, otherwise you would have too high degree of the field extension. So ramification on the x side and branching on the y side correspond somehow to the deviation of this rule that a map of degree n should map n different points to one single point. Equipped with all of this, we can state the Riemann-Hurwitz formula. So we take x and y as usual, smooth irreducible projective curves, and we take f to be a finite, separable, tamely ramified map from x to y. Finite means what I explained a few slides ago. Separable means that the field extension that this defines is separable, a separable field extension. Tamely ramified means that the characteristic of K doesn't divide any ramification index. We also assume, to avoid problems with the characteristic, that it's either 0 or greater than the degree of f. As usual, we are working over an algebraically closed field of characteristics satisfying this. So the theorem is that the canonical divisor of x is linearly equivalent to the pullback of the canonical divisor of y plus r, where r is the so-called ramification divisor of f. So it is a divisor in x formed by this formal sum, where at each point I take x with multiplicity ex minus 1. And remember, this is different from 0 only at finitely many points, because there are only finitely many ramified points. So this is indeed a divisor. So if you do not remember the definition of the canonical divisor or of these constructions, you can go back to the lecture on divisors. From this, we deduce the following corollary that is known as the Riemann-Hurwitz formula. And by the way, the proof of this theorem uses sheaves of Kähler differentials that we will get to in the future, hopefully. So if now our curves x and y have genus gx and gy, then from the theorem it follows that 2gx minus 2 equals the degree of f times 2gy minus 2 plus this thing. And how do we get this? Well, we know that this is the degree of kx, this is the degree of ky, the degree of f is the degree of f, and this is the degree of this divisor by definition, where I'm just summing these integers. And so this says that the genus of x is related to the genus of y via the degree of f, but there is some correction I have to make in case I have ramification, and I have to add this degree to compensate for the loss that happens at points of ramification. And the fact that the degree of the canonical divisor is 2g minus 2 follows from the Riemann-Roch theorem, and we deduced this in that lecture. Let's look at some consequences of the Riemann-Hurwitz formula. So if we have two curves and a map f as before, then the genus of x is at least the genus of y, and we have equality precisely if the degree is 1, or if f is unramified and both genera are equal to 1. Why is this true? Well, look at this formula and solve for the degree of, solve for the genus of x. Then you will find that it is some positive multiple of the genus of y plus some positive number. So this will indeed show that the genus is greater than the other genus. And by looking at the difference, you can see when this is an equality. I leave the details to you. Another consequence is the theorem known as Lüroth's theorem. And it says that if you have the field, the purely transcendental extension of degree 1 over k, and you have a subfield that is not k itself but contains k, then it is of the form of the same form, ks, for some s in kt. So we can prove this. So this follows from Riemann-Hurwitz if the extension is separable. How does it follow? Well, we assume that we have f, a map from P1 to some curve y with the field of fraction of y being this L. By this assumption, this satisfies the previous assumptions, assuming also that the extension is such that all of that holds. But then this y has to have genus 0. Why is that? Well, because the genus of P1 is 0, and so by the previous corollary, this implies that the genus of y is 0. And then, in fact, this implies, even though we are not discussing this right now, that y has to be isomorphic to P1, which means that the function field has to be of this form for some s.